Hello everybody. This video starts the second chapter of this course when we will discuss Turing machines, what they can compute, what they cannot compute, how do they relate to other models of computations, and some connections to logic, foundations of mathematics, and compression. What we're going to see in this video is an overview of the class, but you can also use it as a roadmap throughout this chapter, and also as a summary when you finish this chapter to look back and to wonder what we've done and kind of to see the bigger picture. So we're going to define Turing machines, to introduce Turing machines, which just like finite automata has a constant number of states, of internal states. But unlike automata, they have in addition a large amount of external memory, which is this read-write tape. And in addition, they don't go over the input from left to right once. They can go forward and backward. And this will also means that they don't necessarily need to accept or reject any string. For some strings, Turing machines will just run forever, and they will loop. And this means that in addition to accept or reject, you can also have these loops. And therefore, we need to be a bit more subtle in asking what kind of languages the Turing machines compute. We'll have two notions. One is recognizable and then decidable languages. Languages that a Turing machine can recognize and others that they can decide. And we'll discuss that. We'll also look at variants, possible variants of Turing machines. Some of the definitions in Turing machines are pretty arbitrary. And we can say, okay, what happens if we change these definitions? Do we get something that's stronger or weaker? And we'll see that most of these natural variants are equivalent to Turing machines. And in fact, and this is the Church-Turing thesis, so far, we haven't seen any example of a natural machine that cannot be simulated by a Turing machine. So the Church-Turing thesis is that anything that can be computed by a reasonable model of computation can also be computed by a Turing machine. And this is not something we can prove or will try to prove, but this is an hypothesis that so far we don't have any evidence against. We'll also discuss in this vein non-determinism, non-deterministic Turing machines. These are not exactly a variant of Turing machine because it's not exactly a model of computation. What are these guesses? Where did they come from? But Turing machines will be, in some sense, equivalent. Non-deterministic Turing machines will be equivalent to deterministic Turing machines in the sense that whatever can be recognized by a non-deterministic Turing machine can also be recognized by a deterministic Turing machine. So yet again, non-determinism doesn't add a lot of power. And this will change when we look at the third chapter of our class that will discuss efficiency. So with efficiency, the picture will look very different. Then we will point out and show a simple property that Turing machines can be encoded. But once, so there is for every Turing machine, there is a string that can represent it, a bit string. And this simple observation fact has pretty important corollaries. So one is that we can start discussing problems, computational problems about computation, about Turing machines. So we can have a Turing machine that gets as an input a description for another Turing machine. And we can ask if that input Turing machine, for example, halts on a particular input. In addition, this will allow us to talk about this notion of universal Turing machine that can simulate any other Turing machine. This is kind of a separation between software and hardware in this very, very basic model of Turing machines. We will then start talking about what Turing machines cannot do, just like we did with finite automata. And we'll show that there are languages that are not recognizable and not decidable. Our initial argument will be very simple. It will be a counting argument. We will just show that there are not enough Turing machines to compute every language. So there are more languages than Turing machines. Therefore, many, many languages do not have Turing machines that compute them. But this would not satisfy us because we want to see that there are languages we care about that cannot be computed, and we'll see some simple ones. We'll see mainly ATM that we'll discuss later, but also the halting problem that cannot be recognized, cannot be decided. And we'll also look at other simple problems that cannot be recognized. And the argument, the basic argument for showing it is what's known as a diagonalization argument. And we will see how that works. Once we have our foot in the door in the form of a problem that cannot be computed, we will show that there are many other problems that cannot be computed. And this will be done through this notion of a mapping reduction, where we connect the hardness of one problem to the other by showing that you can reduce, in this picture, problem A to B. And we will use it to show impossibility, to show that some things are hard to compute. In particular, if B is not decidable, then A will not be decidable as well. And we will mainly see other problems about computation that cannot be computed, cannot be decided. But we will see at least one example of another problem that is not obviously about computation. We will move on to Rice's theorem that will give us a strong tool to show at once that many problems about computation cannot be decided and some of them cannot be recognized without having to come up with a different mapping reduction every time. So we will see conditions under which problems about computations are hard. Finally, we will look at a stronger notion of reduction known as Turing reduction or Oracle reduction. We'll talk about Oracle machines. And through that, we will be able to show an hierarchy of hard problems. In some sense, we'll show that for every problem that is hard, there is a problem that is harder. And it's harder in the sense that even if you gave me a machine for free that solved this problem that is hard, the other problem will still be hard. And we will conclude with a few implications and connections of this theory that we discussed and uncovered about computability. We will show that Turing machines can be assumed to have access to their own code. So a Turing machine can know itself, can know its own description, and Turing machines can reproduce themselves by printing out their own code. So this will be kind of a cool property of Turing machines, but we can also use it and will use it. Then we will discuss this idea of the attempt to base mathematics, the foundations of mathematics on very clear logical systems and potentially to automate these systems. And we will show serious difficulties or impossibilities with respect to this agenda, in the sense of the limitation of logical systems that are supposed to capture mathematics and the limitation of the attempt to automize them. Finally, we will talk about Kolmogorov complexity, which is kind of a universal theory of compression of information, how much information there is in a fixed string, and this will be closely related to Turing machines and would conclude this chapter of the course. Thank you.